Hello, I'm Larry Veilleux. I'm a solutions architect at SAC. I lead the training and consulting services for automotive cybersecurity at SAC. I hope you will enjoy this presentation I put together on automotive cybersecurity and the ISO SAE 21434 standard. In this 1-hour session, we'll dive into the world of automotive cybersecurity, why it matters so much these days, and what's being done about it through standards and regulations. We'll go over the ISO SAE 21434 standard and UN ECE Regulation 155, which are built on functional standards of ISO 26262 to mitigate the cybersecurity risks throughout the entire vehicle lifecycle. During this session, we'll cover an overview of automotive cybersecurity and why do we need it, standards and regulations, and what's being done about it, and finally walking you through a practical example of threat analysis and risk assessment, or TARA, for automotive systems. By the end of this session, you will know how to minimize your organization's risk via future-proofing your automotive cybersecurity. I'm looking forward to meeting you soon. Yes, it is possible to hack into a car now. As cars become more software-defined vehicles, or SDVs, they also become bigger targets for cyber attacks. Three main factors creating vulnerabilities are more lines of code lead to more vulnerabilities, increased connectivity provides more potential entry points, also referred to as attack vectors, and vehicle E/E, electrical and electronic systems, also referred to as ECUs, are highly interconnected, so one exploit can spread throughout the entire vehicle. Most exploits come from hackers, but some also come from owners who use similar techniques to unlock features rather than pay monthly subscriptions. These feature hacks cost manufacturers revenue and create new exploits. Securing SDVs is a huge challenge because cybersecurity is dynamic. As soon as one vulnerability is closed, hackers will find a new one. UN ECE regulations now require automakers to implement cybersecurity and software update management processes. While this is a good start, and really we are still in the starting stage, regulations remain open to interpretation. Therefore, ISO standards provide more concrete guidance. Ultimately, everyone must be more aware of cyber risks in vehicles. What we've learned from computers should be applied to cars where the impacts can even be life-threatening. The race for security is endless, but awareness and vigilance will help. To put it in perspective, consider this from a recent episode of the Navy SEALs television series. The episode was about the team deploying to Colombia to thwart an intentional nuclear disaster by an infamous group in Venezuela. To do this, they needed to take out the group's leader, and their strategy was to take control of his car. The dialogue goes like this. Team leader Jason says, "Tomorrow we take this guy out. Davis, how long will it take you to install the vehicle's hacking software?" Davis responds, "A matter of seconds for a stationary vehicle. The signal routes through the Bluetooth on his mobile cell phone and into the car infotainment system, and the driver will have no clue." The intention is to take control of his car and drive it off a bridge, effectively taking him out and thwarting their plan. While this story is fictional, don't underestimate it ever happening before, and it will happen again. This example from an attack vector-based approach would have a high attack feasibility rating, since it is using the car's cellular network connection, making the navigation ECU directly connected and accessible to anyone on the internet. But there are more localized ways of attacking a vehicle, from using devices to simulate a car's key fob, pairing with Bluetooth, or directly accessing a USB or ODB port. Obviously, the latter would require physical access to the car, resulting in a very low but still existent attack feasibility rating. As mentioned before, there are many ways of breaking into and hacking a car, both physical and over the air. From a cybersecurity perspective, these ways are referred to as attack vectors and lead to a vehicle's vulnerability to attacks. And these vulnerabilities can allow attackers to commit code execution on the automobile. Attack vector is a specific path, method, or scenario that can be exploited to break into an IT system, thus compromising its security. Of course, the IT system we are discussing here is a car's electrical and electronic systems, or ECUs. Automotive attack vectors include the following: over-the-air, or OTA, using Bluetooth, Wi-Fi, cellular, and even key fobs, and physical connections and networks, including CAN bus, ODB, LIN, FlexRay, and even automotive Ethernet. Now, the attack surface of a software environment is the sum of all the different points for attack vectors where unauthorized user, the attacker, can try to enter data to or extract data from an environment. Keeping the attack surface as small as possible is a basic security measure. Unfortunately, from this perspective, the number of attack vectors, and therefore the attack surface, is increasing over time. Next, the attack path is a set of deliberate actions to realize a threat scenario, and the attack feasibility is an attribute of an attack path describing the ease of successfully carrying out the corresponding set of actions. Finally, autonomous driving is extending and exacerbating this situation. Autonomous driving requires a lot more and continuous communication with the car's environment. V2X communication, or vehicle to anything, refers to the exchange of information between a vehicle and various external elements such as other vehicles, V2V, infrastructure, V2I, pedestrians, V2P, networks, V2N, and power grids, V2G, to name some. As a result, these advanced communication systems provide a larger attack surface for cyber attacks. An electronic control unit, or ECU, also known as an electronic control module, or ECM, is an embedded system or computer in automotive electronics that controls one or more of the electrical systems or subsystems of a car. Modern vehicles may have as many as 150 ECUs. Automotive ECUs include those such as engine control module, power control, transmission control, brake control, body control, suspension control, navigation control, as well as the infamous infotainment system. The navigation ECU, sometimes referred to as the infotainment system, encompasses cellular, GPS, Wi-Fi, Bluetooth, and USB modules to provide connectivity with external networks and devices. This module helps in establishing services like navigation, internet connectivity, and smartphone integration with the infotainment system. This module also represents a large attack surface, and as mentioned before, it generally leads to the highest attack feasibility rating since it can be accessed remotely. These days, cars are computer centers on wheels. Today's vehicles can contain over 100 computers and millions of lines of software code. These computers are all networked together and can operate all aspects of your vehicle. Computers in one category often need to communicate with computers in another category. For example, the safety system must be able to control the drivetrain and the infotainment systems. One difference between the network in your car and a typical computer network is that generally all devices in the car trust each other. Therefore, if an attacker can access one computer, they can easily access other computers in the car. And this is our objective to change. Examples of in-vehicle networks, or IVNs, include CAN bus, or controller area network, LIN, or local interconnect network, FlexRay, MORE, and automotive Ethernet. And not all are depicted here, nor will I get into any details of why one technology may be used versus another. These IVNs are networked together using a central gateway. Like an Ethernet bridge, the central gateway can act to filter and forward information between systems. They also convert between one speed or another, such as CAN versus CAN-FD, or even between disparate technologies, such as CAN and FlexRay. Typically, the central gateway will include the onboard diagnostics, or ODB connector, either onboard or adjacent to it, which collects data from most embedded systems. ODB is a term referred to a vehicle's self-diagnostics and reporting capability. ODB systems give the vehicle owner or repair technician access to the status of the various vehicle subsystems. As an attack vector, the ODB connector would require physical access to the car, similarly to all the IVN technologies, but don't rule them out. As far as the centralized nature of the gateway, it also provides a good point to implement intrusion detection systems, or IDS. The IDS detects external attacks on ECUs and networks in the automobiles, collects them, and sends them to a backend at the vehicle manufacturer, also called a Security Operations Center, or SOC. Finally, rather than just an IDS, an intrusion prevention system, or IPS, is a system that not only detects attacks, but also responds to them to prevent potential damage. How can we ensure a vehicle is secure? The answer is, well, as good as it can get, considering a hacker will always find a way. There will never be 100% assurance that all risks can be mitigated. The very definition to mitigate is not to eliminate, rather to make less severe. Therefore, we operate under the notion of acceptable risks. As a result, the industry and governments have been working on solutions to make sure that a vehicle is secure by design, to try and avoid the risk to begin with. Note that the industry develops standards and governments develop regulations. More on this next. But before we do, consider this. From an attacker's perspective, an autonomous driving system consists of 3 attack layers: sensor layer, communication layer, and control layer. The sensor layer includes sensors that continuously monitor vehicle dynamics and the environment, but are vulnerable to eavesdropping, jamming, and spoofing attacks. The communications layer includes both near-field and far-field communications to enable communication between edge sensors in the vicinity and remote edge data centers. This layer is vulnerable to man-in-the-middle and Cybele attacks. The control layer at the top of the hierarchy enables autonomous driving systems functions such as automating the vehicle's speed, braking, steering. Attacks on the sensor and communication layers can propagate upward, compromising the functionality and compromising the security of the control layer. Finally, the most important security measures that can be implemented as part of security by design include encryption of data transmissions, authentication of communication participants, regular updating of software and firmware, and the use of intrusion detection or intrusion prevention systems. As mentioned previously, industry and governments have been working on solutions to make sure that a vehicle is secure by design, to try and avoid the security risk to begin with. Note that the industry develops standards and governments develop regulations. By the way, these are tongue twisters, so get used to me saying ISO for ISO, SAE for SAE, and UNCE for UNECE, and their definitions mentioned here on the slide. ISO and SAE develop standards, while UNCE develops regulations. Road vehicles in the context of ISO SAE 21434 and UNCE's World Forum for Harmonization of Vehicle Regulations, Working Party WP.29, Regulations 155 and 156 are those that pertain to the following vehicle categories. A vehicle category classifies a land vehicle or trailer for regulatory purposes. UNCE categories that apply to R155 and R156 are M, vehicles having at least 4 wheels and used for the carriage of passengers, a standard car with 2, 3, or 4 doors, and also buses. N, power-driven vehicles having at least 4 wheels and used for the carriage of goods, trucks and vans. O, trailers, including semi-trailers, as long as it has at least 1 connected ECU. And T, agriculture and forestry tractors, applies to R156 only. Starting with standards, let's look at what's being done by the industry. ISO standards can prepare a value chain for compliance and serve as justification in court with work products as evidences. More on work products later. ISO SAE has developed a standard, ISO SAE 21434 and ISO 24089, to make sure cybersecurity tactics are considered throughout the vehicle's life cycle. This is from conception to decommissioning, and of course, everything in between. ISO SAE 21434 is the baseline for complying with UNSI Regulation 155. As such, an organization must have a compliant cybersecurity management system, or CSMS. ISO 24089 is the baseline for complying with UNSI Regulation 156. As such, an organization must have a compliant software update management system, or SUMS. ISO 24089 and UNSI R156 are mentioned here, but will not be covered in any detail. Following, we will discuss ISO SAE 21434 in more detail. From a governing perspective, the UNSI has developed regulations 155 and 156, which are new cybersecurity regulations for vehicles. R155 is concerning the manufacturer's CSMS, and R156 is concerning the manufacturer's SUMS. Soon, all vehicle manufacturers, OEMs, will need to comply with these in order to sell their cars in European and Asian member countries for sure. For new vehicles from July 2022 and all vehicles from July 2024. ISO standards can prepare the value chain for compliance, and associated work products are essentially documentation, evidences, to serve as justification in court should something go wrong. UNSI R155 regulation translates into domestic laws governing vehicle registration in all countries party to the UNSI 1958 agreement. Because there is relatively high degree of discretion regarding how regulations are interpreted, the UNSI also provides further documentation to support interpretation. OEMs must prove that they have a CSMS in place and must demonstrate its effectiveness in use, and they must continuously review and maintain them. This must be verified by a technical service agency and certified by an authority such as KBA in Germany. In UNSI countries, a car E/E architecture with the specified cybersecurity properties cannot be approved according to homologation requirements until it has gained a valid CSMS certification. Software updates, as per UNSI R156, have strong overlaps with cybersecurity. Unknown vulnerabilities introduced in software are usually discovered by hackers when something special happens, and this is then exploited as a route to launch an attack. Since almost all vehicles' ECUs allow software to be reloaded, updates are a good way to fix software vulnerabilities. It is assumed that software updates are a given, and is therefore not discussed in detail here on how they are implemented. This slide depicts geographically the UNSI member countries as per the 1958 agreement. They include most European countries, some African countries, Australia, New Zealand, Japan, and South Korea. For the most part, each country has its own technical service agency, as mentioned previously, for OEMs to obtain type approval to sell their cars, also referred to as homologation. Each member country recognizes each other's technical service, so approval in one country will translate to approval for all countries. Note that the US and China do require their own form of type approvals. They just have their own ways of going about it. In this section, I will go over the ISO SAE 21434 in a little more detail by discussing each clause individually. Note that ISO SAE 21434 does not differentiate between internal combustion and electric vehicles, or even flavors of hybrids for that matter, since it does require diligence regarding cybersecurity for the entire vehicle life cycle, from concept to decommissioning, and of course, including operations and maintenance phases. For EVs, that also includes charging infrastructure, also referred to as vehicle-to-grid or V2G. In short, ISO SAE 21434 addresses the cybersecurity perspective and engineering of E/E systems within road vehicles of type M, N, and O, as mentioned previously. Today, E/E systems exist in large numbers for all types of vehicles. And moreover, since vehicles also include V2X capabilities for communicating with mobile apps, navigation systems, and OEM dealership backend cloud-based systems for telemetry and such, risks are higher and more widespread. ISO SAE 21434 is really a suite of processes and work products generation that needs to be followed in order to comply with UNSI Regulation 155. It is organized into 15 chapters or clauses and 8 annex items, including an extensive bibliography. Clauses 1 through 4 cover some generic information up front, as is the case with most standards. Clauses 5 through 15 include the requirements that must be followed and their corresponding documentation or work products. Whereas all requirements clauses should be equally adhered to, you will see as I cover each on the following slides that the bulk of the time and effort are spent regarding Clause 9, concept phase, and Clause 15, threat analysis and risk assessment, or TARA. This table was reproduced from the ISO SAE 21434 standard. As we cover each clause following, I have included a smaller version of it in the lower right-hand corner, highlighting the relevant section that is being addressed. Annexes A through H are informative as opposed to normative, which means that they do not specify any specific requirements. Rather, they provide supporting information to the reference normative clauses. Those references are included here. The context for each annex item is as follows. Annex A includes a table that provides a summary of the cybersecurity activities and their corresponding work products that can help an organization to manage their activities. Annex B includes a table that provides examples of weak and strong cybersecurity culture. Developing a strong cybersecurity culture is something every organization should be concerned with. Annex C provides an example of cybersecurity interface agreement templates that can be used by different organizations, OEMs, and suppliers that are participating in distributed cybersecurity activities. Annex D provides example methods and criteria, a decision diagram, to determine if an item component is cybersecurity relevant. Annex E describes cybersecurity assurance level, or CAL, a classification scheme that can be used to specify and communicate a set of assurance requirements, or how rigorous does the protection of the asset need to be. Annex F provides examples of criteria for impact rating and damage scenarios involving safety, financial, operational, and privacy damage, or SFOP. Annex G provides guidelines on how the following approaches can be used for attack feasibility rating. That is attack potential based, CVSS based, attack vector based. Annex H can aid in the understanding of requirements of the documentation by presenting examples of applications of TARA methods in an abstracted and simplified manner. Provisions and work products are assigned unique identifiers consisting of a 2-letter abbreviation. RQ is for requirement, which means shall or must, of which there are 101 total. RC is for a recommendation, which means should, of which there are 13 total. PM is for permission, which means might, of which there are 4 total. WP is for work product, which relates to the documentation of requirements, of which there are 42 total. See Annex A regarding how cybersecurity activities, subclauses, and requirements are mapped to their corresponding work products. Speaking of work products, I have taken the liberty to include a reference to them on the associated slide for each clause. 1 through 3 include generic information, which is common for most standards. Clause 1 states that this document specifies engineering requirements for cybersecurity risk management regarding concept, product development, production, operation, maintenance, and decommissioning of E/E systems in road vehicles, including their components and interfaces. Clause 2 states that ISO 26262, Road Vehicles Functional Safety, Part 3 Concept Phase, is referred to in the text in such a way that some or all of their content constitutes requirements of this document. Clause 3 includes terms, definitions, abbreviated terms, providing a common language for communicating and managing cybersecurity risk. Certain terms, such as cybersecurity goals, are either vague or used differently in other contexts. It's necessary that we are all communicating the same and that there are no misunderstandings. ISO 26262, titled Road Vehicles Functional Safety, is an international standard for functional safety of E/E systems that are installed in road vehicles. Part 3 Concept Phase applies to ISO SAE 21434, for which there are similarities and differences. For example, 26262 refers to fuchsia or functional safety versus 21434 refers to CySec or cybersecurity. 26262 discusses ASILs or automotive safety integrity levels versus 21434 discusses CALs for cybersecurity assurance levels. And 26262 discusses HARAs, hazard analysis, and risk assessments versus 21434 discusses TARAs, threat analysis and risk assessments. Finally, 26262 discusses HAZOP, or hazard and operability analysis, as a method that is often used in the system safety engineering. Rather than HAZOP, 21434's method is THWRP, threat and operability analysis. A THWRP is similar to a HAZOP, except it considers potential threats rather than potential hazards. The overall cybersecurity risk management of an organization described in the document applies throughout the lifecycle phases as illustrated here. These phases are applicable to clauses 9 through 14. Cybersecurity risk management is applied throughout the supply chain, but ultimately the responsibility falls on the OEM, who is responsible for UNSI R155 compliance. However, suppliers and OEMs agree on the work split so that the applicable cybersecurity activities are performed. More on this in Clause 7. An item comprises all electronic equipment and software which are components in a vehicle involved in the realization of a specific functionality at the vehicle level, such as braking. An item and its components interacts with its operational environment. In other words, other items that also have shared connectivity. Really, though, this document describes cybersecurity engineering from the perspective of a single item. If cybersecurity activities described in the document are performed on items and components, then unreasonable vehicle cybersecurity risk is addressed. As we work our way through the subsequent clauses 5 through 15 in the presentation, the concepts and relationships depicted here will become clear. Organizational cybersecurity management requirements include the following. Overall, an organization, or OEM, must develop and maintain an overall framework for their cybersecurity activities. UNSI R155 refers to this as a Cybersecurity Management System, or CSMS. Most importantly, an organization must employ a culture as well as systems and processes conducive to the awareness and sharing of cybersecurity information. Organizations should implement a role or team that has the competencies to conduct regular audits, develop a cybersecurity training concept, and rollout of awareness activities. Also have an alignment over several departments to ensure a secure value chain and a secure product. Everyone must work together up to and including the directors and executives implementing an overall governance policy. It is important that organizations should define and manage a tool chain for the integration of cybersecurity tools within the existing tool chains and processes. Establish central roles and responsibilities, especially accountability, for the product's cybersecurity. And finally, an organization should produce an organizational cybersecurity audit report either internally or with the help of a third-party audit organization, perhaps preceded by performing a gap analysis to keep check on where they are at. Product development cybersecurity management requirements include the following. The organization must find somebody who is willing to carry the responsibility for the entire product security. Accountability is key to achieving this. Security artifacts must be aligned with the product development and deployment process to ensure the timing and coordination of all work products. Sometimes aspects of the product will need to be tailored to meet the cybersecurity goals. The lifetime of the product should be defined in the concept and development phases, which are outlined in Clause 9 and Clauses 10 and 11, respectively. To determine their effectiveness, the organization should perform regular cybersecurity assessments of their cybersecurity plan and case, the latter of which is a structured argument supported by evidence to state that the risks are not unreasonable once the appropriate cybersecurity controls are in place. And the cybersecurity plan is what in particular is required to maintain the concept in a concise way and maintain this throughout the vehicle's life cycle. More on concept when we discuss Clause 9. Distributed cybersecurity activities refers to OEMs working with their suppliers through mutual cooperation. The most important thing to note is it's the OEM and not the suppliers who are responsible to meet the regulation requirements to obtain type approval for their vehicles. If the development of an item requires distributed cybersecurity activities, a cybersecurity plan should be defined to align responsibilities and to define interfaces between the involved parties. As a result, a cybersecurity interface agreement, or CIA, should be agreed on and documented. Assessment of cybersecurity capabilities will help to prove cybersecurity capabilities of suppliers are addressed by means of self-assessments, audits, certifications, and maturity assessments. This helps build trust between the OEM and its suppliers. Finally, distributed activities require the consolidation and aggregation of work products, and the sharing of information should be defined at the beginning of the cooperation. Continual cybersecurity activities and requirements include the following. The organization should identify relevant input sources for cybersecurity information and create capabilities to analyze and manage cybersecurity information. The organization should have processes and methodologies implemented which allow for the handling of new vulnerabilities. All involved parties of the value chain should focus on an efficient implementation of vulnerability management, including the consideration of necessary capabilities for the existing and upcoming product portfolio. This needs to be determined in early phases of product development, since relative to the risk mitigation, not all security measures can be implemented after a product is released, since some products may not be field updatable. The product lifecycle consists of Clause 9, concept phase, Clauses 10 and 11, development phase, as well as Clauses 12 through 14, post-development phase, consist of production, operation, and decommissioning. More specifically, Clause 9 concept includes activities that determine cybersecurity risks, cybersecurity goals, and cybersecurity requirements for an item. Clause 10, product development, includes activities that define the cybersecurity specifications and to implement and verify cybersecurity requirements. Clause 11, cybersecurity validation, includes the cybersecurity validation of an item at the vehicle level. Clause 12, production, includes the cybersecurity related aspects of manufacturing and assembly of an item or component. Clause 13, operations and maintenance, includes activity related to cybersecurity incident response and updates to an item or component. In Clause 14, end of cybersecurity support and decommissioning includes cybersecurity considerations for end of support and decommissioning of an item or component. And finally, each of these phases will be discussed in more detail, starting with Clause 9 next. Clause 9 concept phase is broken out per item definition and cybersecurity goals, claims, concepts, and case. It starts with the item definition, which identifies the item and its operational environment. The item definition forms the basis for the subsequent activities. Cybersecurity goals refers to figuring out what we're trying to secure, at least if it needs to be secure, what kind of attacks to look out for, and provide a baseline example of how to deal with them. This will lead to the protection of assets that, if compromised, would lead to a damage scenario. Cybersecurity risks are assessed using TARA, and more on this when we discuss Clause 15. Cybersecurity claims refer to which risks that cybersecurity goals do not account for, but are still applicable to the scenario. Let's say that there is a fail-safe mechanism built in such a way that if someone was to try an unauthorized flash of an ECU, for example, not preventing them from trying via a cybersecurity goal, that the ECU would lock itself from further flashing for 10 days. As per ISO SAE 21434, the cybersecurity claim can include a justification for retaining or sharing the risk. Cybersecurity concept refers to how we want to make sure or verify that the cybersecurity goals are measurable and achievable to ensure conformance with these goals. In other words, determine your risk treatment options. So implement a control, which is a measure that is modifying risk as defined by a cybersecurity goal, and test that it's successful. Also verify the consistency and compatibility with the item's function. Finally, a cybersecurity case is an argument and evidence regarding your cybersecurity concept, really to state that the remaining risks are not unreasonable. Product development challenges include the following. Depending on your organization, it is possible that various development approaches can be used within a project. In such case, you have to identify synchronization points and align work packages. The validation of work packages requires deep knowledge about the used methodology as well as the products and their connections to the ecosystem. If possible, a suitable tooling supports the validation process and ensures the required quality standard. Test cases will become particularly important in the future. The development or testing team has to include the verification of requirements, but also of non-functional test scenarios. Regardless of the development methodology, milestones and synchronization points between departments and disciplines should be implemented to avoid redundancies and inconsistencies and develop best practices approaches. So Clause 10 is used to determine that the product is built right, whereas Clause 11 helps to determine that the right product is built. During cybersecurity validation, the item is considered in its operational environment at the vehicle level, along with the configurations intended for series production. The objectives of Clause 11 are to, 1, validate the cybersecurity goals and cybersecurity claims, 2, confirm that the item achieves the cybersecurity goals, and 3, confirm the adequacy and validity that no unreasonable risk remains. Production challenges include the following. The main responsibility of the production team is to ensure that the final product will meet all the requirements and specifications as defined by the development department. At this point, the security of the used tools within the production is important. The organization should define a process or default remediation actions to react on incidents and to reduce their impact to a feasible minimum. Processes for software update management must be implemented to ensure a consistent level of security. Thus, also cybersecurity features can be included in the default release plan. Especially in the context of data protection, the question of decommissioning will grow in importance. The organization must include customer communication mechanisms to inform the user about the end of support and about decommissioning. Operations and maintenance challenges include the following. In addition to design protections, the automotive industry should establish rapid vehicle cybersecurity incident detection and remediation capabilities. Such capabilities should be able to mitigate safety risks to vehicle occupants and surrounding road users, or RUs, when a cybersecurity attack is detected, and to transition the vehicle to a minimum risk condition as appropriate by the identified risk. Communication is key both from a remediation perspective, but also to help preserve an organization's reputation. The worst case scenario is to try and cover up incidents or to do nothing in response and just hope it goes away. Decommissioning is different from end of cybersecurity support. An organization can end cybersecurity support for an item or component, but that item or component can still function as designed in the field. Both decommissioning and end of cybersecurity support can present cybersecurity implications, but those implications are considered separately. Decommissioning can occur without the organization's knowledge and in such a way that the decommissioning procedures cannot be enforced. Therefore, the act of decommissioning is out of the scope of the document. If cybersecurity support and decommissioning are considered in the concept and product development phases. Appropriate documentation, for example, instructions and user manuals relating to such requirements, can enable decommissioning with regard to cybersecurity. Finally, when you turn in your car for resale, or let's say you had synced your smartphone with a rental car, similar decommissioning procedures such as deleting all your data from the infotainment system should be followed. I suggest that you think twice about pairing your mobile phone with a card that is shared. There are other more secure ways to charge your mobile device. TARA covers the risk evaluation and assessment methods, as well as the treatment and planning of identified risks. These methods are aligned with NIST SP 800-30 and ISO IEC 31010, which deal with attack feasibility, the likelihood, and associated impacts. The output of a TARA will indicate a high, medium, low, or very low risk rating, but without proper definition of risk tolerances, caution, and established baselines, the organizational usefulness will be limited. TARA challenges include the following. The assets of an item that are considered during the TARA often already exist in reference repositories or model. It is a challenge to avoid duplication of models, but it might be needed to synchronize and reuse existing architectural elements and requirements. TARAs of large connected systems may consist of hundreds of elements with interdependencies within the operational environment. Furthermore, we need to trace input data, for example, existing system models and outputs such as derived requirements from security controls and reports. Controls and attacks include feasibility ratings that yield in combination with the potential impact of a risk value. It will be challenging to get comparable and reproducible results among a set of analyses, since the given rating is subject to the analyst and may vary even for similar entities. Performing TARAs is an iterative process. In each iteration, the item as well as the corresponding threat scenarios and mitigations might change. It is a challenge to keep track of the controls, the implementation status, and related requirements over time. I will drill down to performing a TARA in the next section. In this section, I will discuss how to perform a TARA in more detail. This is essentially ISO SAE 21434 Clause 15 for threat analysis and risk assessment. It should be noted that TARAs are executed separately on each item, where some items have much more complexity than others. That and the fact that TARAs for multiple items can be combined into a model or project that reuses catalogs, methods, and definitions, which essentially makes the spreadsheet approach unwieldy. Therefore, it is better to use a model-based application instead. The application I used in the following slides is the Itemist Secure application. Road vehicle cybersecurity, or just cybersecurity, is a condition in which assets are sufficiently protected against threat scenarios to items of road vehicles, their functions, and their E/E components. An item is an asset to be protected, such as the integrity and availability of the braking system. Once the assets are identified, the impact of the damage will help determine how bad the damage will be. Each damage scenario is inspected to determine the feasibility of the attack, which is how likely it is to occur. And finally, based on the level of damage and the likeliness of it to occur, a risk level is determined, which is essentially the effect or uncertainty of an attack. As a result, TARA can be broken down into a 4-step process, and each step will be broken out and discussed separately on the remaining slides. Starting from the item definition, this slide depicts 2 swim lanes, so to speak, one for impact rating and one for attack feasibility rating, and together both leading to a risk determination. Relating back to the previous slide, I will cover the 4 TAR steps in more detail now. The first step is to create the item definition. What is it? What does it do? How does it do it? An item is a component or set of components that implements a function at the vehicle level. This includes the components, data, channels, and functions. Depending on the function of the item, it can include a few or many of these properties. Each of these can be an asset from a cybersecurity perspective. The second step is asset identification and impact rating. Each of the item definition attributes are identified for their assets to be protected. For example, an electronic brake actuator can be analyzed for its integrity and availability should it be the target of a cyber attack. Assets are inspected to determine their security properties using the SAE triad of confidentiality, integrity, and/or availability. Each asset security process leads to a damage scenario, which is evaluated using impact categories for safety, financial, operational, and privacy, or SFOP. And for each SFOP defined, rate as severe, major, moderate, or negligible to determine the impact rating. The third step is threat analysis and attack feasibility rating. Each aspect of the item definition is also inspected to determine what, if any, threat scenarios could apply using threat classes for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privileges per stride. This leads to the specified threat scenarios, which are then associated with damage scenarios from step 2, as well as attack paths or steps to be included. Together, these are referred to as attack trees. Finally, each threat scenario and attack path are rated as high, medium, low, very low, most often using the attack potential-based approach. The fourth step is risk determination and risk treatment. By comparing the impact and feasibility of an attack, a risk level, usually a value between 1 and 5, where 1 is minimal and 5 is the highest, is determined. And finally, one must determine the risk treatment to be used, such as avoidance, reduction, shared or transferred, and acceptance. The impact model defines security properties, impact levels, stakeholders, impact categories, and impact options. An asset is an object that has value or contributes to value and has one or more cybersecurity properties for CIA, whose compromise can lead to one or more damage scenarios for SFOP. A security property is an attribute that can be worth protecting, and this property includes the CIA triad discussed next. An impact category, which is related to the damage scenarios, is an adverse consequence involving a vehicle or vehicle function and affecting a road user, and consequences can be classified under the categories of SFOP. Finally, a road user is a person who uses the road, such as a driver, passenger, pedestrian, cyclist, motorist, or vehicle only. Just note that an OEM could also have its own SFOP properties. Finally, the impact level is an estimate of the magnitude of damage or physical harm from the damage scenario. CIA in this context stands for confidentiality, integrity, availability, the CIA triad, but not cybersecurity interface agreement as previously discussed, or even Central Intelligence Agency for that matter. CIA is the minimum set of properties based on the ISO SAE 21434 standard. In addition, other properties such as authenticity, accountability, non-repudiation, and reliability can also be involved. Current practices also include authenticity for CIAA. For example, set forth by information security, CIA ensures that only authorized users for confidentiality have access to accurate and complete information for integrity, and when required, for availability. Each security property is selected for each parameter of the item definition and will lead to a corresponding damage scenario. Each damage scenario has impact categories with their associated levels. The damage scenarios shall be assessed against potential adverse consequences for road users and the impact categories of safety, financial, operational, and privacy, or SFOP. SFOP is the minimum set of categories based on the ISO SAE 21434 standard and is included in Annex F. Additional categories can be considered, such as R for reputation. In addition to road users, stakeholders can also include OEMs. The impact level of a damage scenario shall be determined for each impact category to be one of the following: severe, major, moderate, or negligible. Considerations on how the scalability of damage, for example, impact to multiple road users in a single damage scenario, can also be included. The typical approach for impact rating is to evaluate it on the 4 SFOP dimensions, and for each damage scenario, the highest impact level of the associated impact category wins. Finally, impact level can be amplified by the impact scale, 1, some, or many. The feasibility model defines the attack feasibility levels, or AFL, feasibility options, and attack feasibility table. Threat scenario is a potential cause of compromise of cybersecurity properties of one or more assets in order to realize a damage scenario. Attack path is a set of deliberate actions to realize a threat scenario by an attacker, which is a person, group, or organization that carries out an attack path. Attack feasibility is the attribute of the attack path describing the ease or difficulty of successfully carrying out the corresponding set of actions. ISO SAE 21434 includes Annex G that provides guidelines on how the following approaches can be applied for attack feasibility rating: attack potential base, which is represented here, CVSS base, or common vulnerability scoring system, and attack vector base. Considerations of whether the attack has the potential to scale, meaning can be easily extended to multiple instances and targets, and represented here as a consecutive attack feasibility, can be included in the rating of attack feasibility. The feasibility model has the attack feasibility levels for very low, low, medium, and high. The attack potential-based approach has feasibility options, which includes categories for elapsed time, includes the time to identify a vulnerability and develop and successfully apply an exploit. Specialized expertise is related to the capabilities of the attacker relative to their skill and experience. Knowledge of the item or component is related to the amount of information the attacker has acquired about the item or component. Window of opportunity is related to the access conditions, type, and time to successfully perform an attack. It combines access type, which is the logical and physical, and access duration, which is unlimited and limited. Equipment is related to the tools the attacker has available to discover the vulnerability and/or execute the attack. These 5 categories are abbreviated as ET, SE, KOIC, WOO, and EQ, respectively, and added up together will determine the attack feasibility level. Next, you will see how the impact level and attack feasibility level are used to determine the risk level. As mentioned before, trying to accomplish this using a spreadsheet approach is unwieldy. Therefore, it's better to use a model-based approach like the examples used here for the item is secure application. A threat catalog consists of threat classes which can be used across multiple TARAs. It eases updating feasibility ratings throughout the entire TARA lifecycle. Threat scenarios may refer to threat classes in order to derive the cause of the compromise. But most importantly, attack steps refer to threat classes and derive the threat classes' feasibility ratings. Threat catalog depicted here comes from the Automotive Security Research Group, or ASRG, Garage, and helps in kickstarting the threat modeling activities. There are 6 threat classes, along with their associated subclasses for STRIDE, which is a model for identifying and categorizing cybersecurity-related threats. STRIDE is broken out as spoofing, relates to the authenticity or impersonating something or someone else, spoofing identity. Tampering relates to integrity or modifying data or code, tampering with data. Repudiation or denial relates to non-repudiation, meaning only you could have done that, for someone claiming to have not performed an action. Information disclosure relates to confidentiality or exposing information to someone not authorized to see it. Denial of service relates to availability or denying or degrading services to users. An elevation of privilege relates to authenticity or authorization to gain capabilities without proper authorization. Notice how each category has its own default feasibility categories, which are also attack potential based, and each can threaten one or more security properties and act on one or more assets. Again, using a model-based approach help to keep all these accurate and intact, especially across one or more TARs. Risk determination is the effect of uncertainty on road vehicle cybersecurity expressed in terms of attack feasibility and impact rating. The risk model defines the risk levels, risk matrix, risk treatment, propagation operations, and feasibility and impact combinators. For each risk, you can also assign an appropriate risk treatment option. By default, we start with 5 risk levels, aligned with ISO SAE 21434 requirement 15-16. Of course, this can be customized based on your organization strategy, and as covered on the last several slides, the risk matrix defines how attack feasibility and impact conclude or propagate to a risk level. The attack feasibility definitions originate from the feasibility model. Impact level definitions originate from the impact model. For each identified risk, you may want to decide for an appropriate risk treatment option. As a starting point, the following options are available: avoidance, reduction, share or transfer, or to accept the associated risk. Since item is secure as a model-based application, then you could also control the propagation operations. For example, the impact level is determined from or propagated from each damage scenario, and the highest impact levels of the associated impact categories wins. As part of the TAR process, appropriate countermeasures should be applied in order to mitigate, eliminate, or reduce the identified risk. We call them controls, and as per ISO SAE 21434, definition 3.1.14, a cybersecurity control is a measure that is modifying risk. Here you can see that the same TARA for an item with and without controls being applied. In this case, the control reduced the risk level from a 4 or medium to a 1 or very low. Not depicted here, but there can also be assumptions modeled which are assuming that certain steps are already being taken. For example, using a tamper-proof ECU enclosure, or that ECU flashing has been protected by XYZ by the supplier so that a hacker would need to hack XYZ, which would be difficult. Assumptions are only addressed indirectly in ISO SAE 21434. The item definition documented in Clause 9.3 of ISO SAE 21434 is a precondition of ATARA, followed by the asset identification that associates with the security properties which lead to damage scenarios and ultimately to the impact rating. Proceeding with the threat analysis that evaluates the probability of the potential attack steps as well as the likelihood to achieve them. In addition, you can analyze the conceivable risks related to your item definition on which you can decide whether this would be acceptable or otherwise appropriate countermeasures have to be applied in order to mitigate the identified risk. We call them controls. Basically, once you have modeled your TARA end-to-end, you will be able to evaluate the impact and attack feasibility, which will result in an overall risk level. Next, I will walk you through each step in more detail. As per ISO SAE Clause 9, Subclause 9.3, the item definition forms the basis for all cybersecurity activities. An item comprises all electronic equipment and software, which are components in a vehicle involved in the realization of a specific functionality at the vehicle level, such as braking. An item and its operational components interacts with its operational environment. In other words, other items that also have shared connectivity. Really, though, the document describes cybersecurity engineering from the perspective of a single item. As you model your item definition, you first determine what is within the item boundary. That is, what is involved with the system that enables it to operate alone. Then you determine what is within the operational environment, meaning how the item interacts with or has connectivity to other items and components in the vehicle. Finally, determine if there are external components that can be used to gain access to the operational environment and ultimately to the item itself. For each of these domains, you will model its structure based on physical components, the logical data, which is essentially the firmware, software, or database of the component, the physical channels, which are the connections between components, and the logical data flows, which are essentially the data packets that flow across the channels. And finally, what function or functions that the item performs. Next, you will determine how these can be assets from a cybersecurity standpoint. Based on the item definition, which consists of a set of functions, components, data channels, data flows, you can decide on the meaningful assets that you would like to cover as part of your TARA. We consider an asset meaningful when breaking it might lead to damages either for the road user or the organization. Now you can really see the modeling effect of the item as secure application. Even though only one of the functions and data are depicted here, each of the properties of the item definition are modeled in a way that you can accept or reject it based on the security properties for CIA. Once accepted, it will propagate to create an associated damage scenario, which we will discuss next. For each damage scenario that was created through the asset identification process, you will associate one or more of the SFOP impact categories. And for each of the SFOP impact categories, you will determine an impact level based on how severe the impact will be. The levels are severe, major, moderate, and negligible. It really depends on the function being modeled because what might be negligible from a safety perspective might be severe from an operational perspective. Since there may be up to multiple impacts associated with the damage scenario, the highest impact is propagated as the resultant impact rating. Threat scenarios are a starting point for the attack path analysis. A threat scenario is a potential, rather high-level attack. It is realizing one or more damage scenarios and is itself realized by a set of attack steps, often referred to as an attack tree. Again, you can really see the modeling effect of the item as secure application. Similar to asset identification, each of the properties of the item definition are modeled in a way that you can accept or reject it based on the threat classes for STRIDE, which are propagated from the embedded threats catalog. Once accepted, it will propagate to create the associated threat scenario, which we will discuss next. For each threat scenario that was created through the threat scenario identification process, you will associate one or more of the item definition, damage scenarios, and attack steps. Each attack step has its own attack feasibility based on the attack potential feasibility categories. Each attack steps can also be mitigated by a control or even an assumption to lower the risk to an acceptable level. As you can see here, since both the impact level and attack feasibility have been defined, these now propagate to determine the risk level auto-magically, since item is secure is a model-based application. For each threat scenario, the risk value shall be determined from the impact of the associated damage scenarios and the attack feasibility of the associated attack paths. And for each threat scenario, considering its risk values, one or more risk treatment options shall be determined. The goal is the identification of risks based on recorded threat scenarios and attack steps. Risks illustrate the risk level present in a threat scenario, attack step, or security control. A risk element can be used to determine the impacted stakeholder, related impact categories, and see the control scenarios side by side. Control scenarios are a unique attribute of the item is secure application and are included in the model. Control scenarios provide a side-by-side comparison of security concepts. An example of how control scenarios would work is to compare the risk level with no controls versus with controls. Or maybe one control is more costly, perhaps in terms of the time and money to implement, but all but eliminates the risk. Remember, a hacker will always find a way. Compared to a less costly control, but only reduces the risk. This, of course, leads us to our next topic on risk treatment, which I will discuss. The risk treatment decision allows tracking of the treatment decisions per risk side by side with the rationale per decision. The available risk treatment decision originates from the risk model in your method configuration. Typical risk treatment decisions are avoidance via assumptions or removal of the threatened asset, reduction via mitigating controls, share or transfer with someone, for example, a supplier, group, or team, and acceptance of the current risk level. So there you have it. I hope that you enjoyed this presentation I put together on automotive cybersecurity and the ISO SAE 21434 standard. Please reach out to me at SAC to discuss how we can help your organization to ensure that your products are secure by design. Thank you for your time.